So today we are looking at, let me move this down. Okay. So today we are in 4.2, which is logarithmic functions. So before we get to logarithmic functions, though, I just want to remind you in 4.1, we did exponential functions. And if you will recall, whether you're talking about growth or decay, it always passes through the point 0, 1. And we had our growth exponential function. And if you will recall, that is y equals b raised to the x when b is greater than 1. And then we had our decay. Oh, I should have done that in a different color. Oh, well. All right. And this, of course, is also y equals b to the x, but this is when b is less than 1. Now, recall that your base is always greater than 0. So this that deals with growth is when you are greater than 1. This that deals with decay is when b is between 0 and 1, like 1/2, 2/3, 1/8, and so forth. Now, one other thing that I want to do is to look at this and say, and ask, what is my domain and what is my range? Now, remember, domain is what your x value can be. So if I look here, here is my x-axis. And if I chose any point on this x-axis, notice as this goes out, your x would continue on here. And as this goes to the left, your x would continue in the negative direction. So our domain is negative infinity to infinity. Now the range is your output or your y-axis. And if you'll notice, y is everything from here and above. Well, if I'm only looking at points here and above the x-axis, that means my domain can only be positive, or I'm sorry, not my domain, my range. So it is from 0 to infinity. So I just want to remind you about that. So that's exponential functions, which is what we did in 4.1. So that's just a quick reminder. So today, what we're going to do is we are going to add to that our log functions. All right, so what we're looking at here is y equals log base b. So I'm going to give you two graphs. Now, I also want to point out on your calculator, you have a log button right here. We're going to be looking at the log button and this button here as well. And I'll tell you what that is here in a little bit. Okay, so we need to look at the scenario where b is greater than 1 and b is less than 1. So greater than 1 is when you deal with growth. So this one is going to be an example of growth. And what you will find, and I'll go to Desmos in a little bit, is this growth function looks like this. Now notice instead of passing through 0, 1, it passes through 1, 0. And so this is, since it's increasing, deals with growth. So here is 1, 0. And when B, or your base, is between 0 and 1, then you are dealing with decay, meaning this decreases. It still passes through the point 1, 0. Okay, now what this looks like in Desmos, I've already graphed. So if you'll notice, log base 3. So 3 is greater than 1. So my red function, if you'll notice, it passes through 1, 0, and it depicts growth. It's increasing. My blue function, I have 0.5 here, and obviously 1/2 is between 0 and 1, so it depicts decay because it's decreasing and it still passes through the point 1, 0. So that's just a review over what those functions look like. So what we then will is expand on that. So kind of an overview of something that you have hopefully seen in the past. And one thing to always remember with your logarithmic functions is it's all about the base. Okay, so you'll see a function f of x equals log base b to the x. So of course that's a function, which means we can then write that as y equals log base b to the x. Now all I'm going to do is I'm going to flip these, because a lot of times you'll see it written as log base b to the x equals y. Now, I want to show you the relationship between the log function and the exponential, and this goes back to it's all about the base, okay? So it is all about the base, and if I was going to rewrite this as an exponential function, we would say b raised to the y equals x. So this is how you can always rewrite a log function to its equivalent exponential function. So let me give you some examples with actually putting some numbers in here. Say you were given log base 2 of 32 equals y. So if we looked at this and we wanted to know what y equals, okay, again, it's all about the base. So I'm going to rewrite this as an exponential function, which means I would write it as 2 raised to the y equals 32. And then I would ask myself, can I rewrite 32 as base 2 raised to some power? We have 2 to the y here. 32 is the same thing as 2 to the 5th power. 2 times 2 times 2 times 2 times 2 is 32. So if we have the same base, then that allows us to say then that, leave room for another example. So we can say y equals 5. All right, another example. See if I can fit this on here. Let's say we have log of the fraction 1/10. Now realize, yes, this is fraction, but this is not what I'm talking about as far as whether you have growth or decay. That is the base. This is not your base. Equals y. Now, one thing about logarithms is if you do not put a base here, so up here I have base 2. We don't have anything written here. It was not given. That being the case, it is always understood to be 10. If it just says log 2 equals y or log 5 equals y, if there's nothing written or given in this base, it's understood to be 10. So again, if I rewrite this as an exponential function, I would have 10 raised to the y equals 1/10. And we know we can rewrite 1/10 as 10 to the negative 1. Therefore, we learn that y is equal to negative 1. Now, that is a refresher, hopefully. What we will be working with is natural logs. And natural logs have a base of e. And if you remember, e is 2.71, on and on and on and on, never repeats, never terminates. So when you have log base e to the x, that is the same thing as ln x. This is called natural log. This is what we're going to be looking at a lot. And if you'll go over to your calculator, I mentioned this button right here. That is your natural log. And if you'll look above it, it has e raised to the x power. So we're going to be using and looking at these two buttons on the calculator. So the first thing we need to do is start learning. I'm pulling out the formula sheet because I want to refer it back to the formula sheet, is we are going to start learning the properties of natural logs. So of course, these are provided on your formula sheet. Now, the reason we are introduced and we learn these properties is because these will be used and applied when the exponent is the unknown. So I'll point that out when we get to it. That might not make a lot of sense right now. Okay. All right. So the first natural log property is that the natural log of 1 is always equal to 0. So anytime natural log of 1 equal to 0. Okay. All right. The second property is the natural log of e equals 1. Now, this is going to come into play a lot. You need to get that memorized. So as soon as you see the natural log of e, you go, oh, that's equivalent to 1, and you can substitute 1 in for it. The third one is the natural log of e raised to the x is equal to x. This is another one to remember. Now, we're actually going to learn here in a little bit another property that I'm going to then come back to this and I will show you how it gets applied. That if you don't recognize or remember this at first, that you can also apply another property and still get to that same answer. And then the fourth one is e raised to the natural log x equals x, and this is true as long as x is greater than 0. Okay, now all of these are on your formula sheet. So if you'll look at your formula sheet, They're all right here. So the good news is you don't have to memorize them. It is nice if you get familiar with them enough that you recognize them, but they don't have to be memorized. But you do have to recognize them to at least know where to go back on your formula sheet. All right, let's look at some examples. The natural log of e raised to the 7th. So if I look over here, the natural log of e, now see up here, it'd be understood that e's do the first power. Re actually has a power of 7, so it's just equal to 7. All right, another example, the natural log of e to the 3x. Well, this is the same property. If you see the natural log of e raised to some power, then it is equivalent to whatever that exponent is. Now, this one you're going to have to be careful because I go, ooh, I have a cube root. I don't see anything over here that has anything to do with a radical. How do I handle that? Well, man, this goes back to what we learned earlier in this course, and that is how to rewrite a root into it with an exponent. Or, sorry, I'm just getting a phone call. Don't need to answer it. So if you recall, we could rewrite this as the natural log of e to the 2/3. Then we can apply this same property, so it just equals 2/3. Let's see, e natural log of 5. So I come over here, e natural log of 5 equals x. My x is 5, so that just equals 5. So that's some kind of very basic examples just to kind of help you get familiar with those properties. All right, so of course, those aren't the only properties. So we have the natural log of m times n. So mn means m times n, and that is equal to the natural log of m plus the natural log of n. I was seeing if I wanted to do an example. I'm going to go ahead with these others first. Okay, the 6th one. The natural log of 1 over n is equal to negative natural log of n. So you can kind of think of this too as, we could rewrite this as n to the -1. So that's where that negative in essence comes from. Okay, the 7th one. The natural log of m, whoops, that should be an m. M over n is equal to the natural log of m minus, goodness, the natural log of n. And then the 8th one, and then this is the one that I'm going to refer also back up to here. So this is the natural log of m raised to the p power is equal to p times the natural log of m. All right, this property right here. Basically what we're doing is we're taking this exponent and we're bringing it out front. So if you recall this right here, rewrite it. So we have the natural log of e raised to the x. So based upon this property, I can take this x and move it to the front. So I would have x times the natural log of e, And then this is where you need to recognize that this is the same thing as 1 because the natural log of e is equal to 1. So I have x times 1, which is just x. So that's why this property is very similar to this. Also, you could take a look at this and you could rewrite this as the natural log of n raised to the negative 1. Ooh, excuse me. I can take this, move it out front, and we would have negative 1 times the natural log of n, which you wouldn't have to show the 1. So that's how that particular property also affects that one. Okay, all right. So let's look at some examples to apply these rules or these properties. All right, so natural log of 2 over 3. All right, so this is 2 over 3, which would be like this property 7, 2 over 3. So I can rewrite this as the natural log of 2 minus the natural log of 3. Now, I want to show you on your calculator. So I'm just going to do the natural log of 2/3. So the natural log of 2 over 3. And you get negative 0.405 and so forth. So when I plug this in, I should get that exact same number. So the natural log of 2, whoops, I guess it wants parentheses, minus the natural log of 3, and lo and behold, I get the exact same number. So you may be thinking, okay, why, if I can plug this into my calculator, why do I need rewrite it as this? Well, we won't always have numbers, and you may be asked to show it in expanded form. This is an expanded form. So it may want you, meaning your assignments, to show that you understand the properties. So you're not actually finding the negative 0.405, but you're just, it's asking you to rewrite it. All right, another example. Natural log of 4 raised to the 7th. All right, so I have an exponent, so this is going to be applying this property number 8, and that can be rewritten as 7 times the natural log of 4. And of course, you can go in your calculator and confirm that those do equal, but we're just right now looking at the properties in general, okay? All right, let's look at the natural log of 3x minus the natural log of 3. Now, what you need to do is recognize this right here as 3 times x. So that would be the same thing as property 5. So I could rewrite this as the natural log of 3 plus the natural log of x, and then I still have minus the natural log of 3. Now, why is that helpful? Because look, natural log of 3 minus natural log of 3. Anything minus itself is 0, so this actually equals the natural log of x in simplified form. Okay, another example. Let me come over here and do it. The natural log of x to the 5th minus the natural log of x squared. Now, what you need to start recognizing is which property would be applied. And so when I look here, I go, oh, that's going to be property number 8. So we're going to look at each of these and bring that in front. So this would actually be the same thing as 5 times the natural log of x minus 2 times the natural log of x. These are considered like terms because they're both the natural log of x. So if I have 5 of something and I take away 2 of them, I'm left with 3, the natural log of x, and that would be in simplified form. Okay? All right. Now, this is All of these properties are what we are going to eventually use when we are working application problems, okay? So as I stated earlier, now the unknown, so what you're looking for, the unknown will be the exponent. Therefore, these three dots in math mean therefore, we will need to apply natural logs. So all of those properties is what's going to help us. Now, before we get there, I just want to remind you the formulas that we previously used. So these four here, we're still going to be using those in this section. So the first one that I want to look at is future value. So A, future value is equal to some money amount P, 1 plus R over M raised to the M times T. And then also, now remember, this is M is how it's compounded. Annually is 1, semi-annually is 2, quarterly is 4, monthly is 12, and so forth. If you have compounded continuously, then the formula we'll use is future value equals P times E raised to the RT, because we don't have M in this one, okay? All right, so what we're going to be looking at is investment increase, meaning you invest money, it increases in value. Now, for a lot of these problems, P is not given. So when P is not given, I'm going to show you what the wording will be and how to handle it, okay? So say we're using the formula P1 plus R over M raised to the MT. P is not going to be given, all right? But what the problem will say is it will say your investment, we just don't know how much we invested, okay? Your investment will be doubled, or you will double your investment. Well, if I'm investing P, doubling that would mean I have 2P. So if this was 5,000, doubling it, I now have 10,000, and so forth. It may say that, and again, this is all the same. It may say that your investment, how long will it take to triple your investment? Well, if this is still P, tripling it would mean 3P. You multiply it times 3. It might say something like your investment to increase by 50%. Okay, well, when it's worded that way, or it might say 60% or 70%, what that means is that by 50%, what you have to think of is P, whatever your initial investment was, that represents 100% of your investment. So if I invested $5,000, 100% of my money is 5,000. If I invested 8,000, then 100% of what I invested is the full $8,000. So 100,000 is equivalent to the number 1, right? If you move the decimal point 2 places. Well, think of increase by 50%. That means that you want your original 100% to increase by an additional 50%. So I move the decimal, that would then be 1.5p. And so if this said increased by 90%, this would be 1.9. If it said increased by 65%, this would be 1.65, and so forth. So that's just going to come in handy as you work these problems. The next example, I want a little bit more room than just what's left on that page. So I'm going to come over here to a new sheet of paper. All right, an inheritance is invested at 12% compounded quarterly. How long will it take for it to double? Okay. So when you are looking at a problem like this, here's some things that you need to look for. Compounded quarterly, this tells me that m is equal to 4. So when you're looking at your formula sheet, then if you're trying to decide whether to use this formula or this formula, this is the formula that deals with m, so I know I'm going to be using this formula. And then 12%, so we know r equals 0.12. And for it to double, so if I'm investing P, for it to double will be 2P. All right, so we know that R is equal to 0.12, M is equal to 4. We know that P is your initial amount invested. And then if that gets doubled, then we know that is 2P, all right? So how long will it take? So we invested that now, so what will be its future value? So we are going to use the formula P times 1 plus R over M times M times T, because notice, let me do a different color. How long will it take? That means it is asking you to find T, okay? Now, this is my initial investment, and we want to know how long will it take for it to double. So that's where the 2P goes in. Now, here's the key on this. Notice there's a P on this side of the equation and this side of the equation. So we're going to divide both sides by P. So in essence, this cancels and we're left with 2 equals 1 plus 0.12 over 4 raised to the 4t. So my P gets canceled out. All right, well, we can add this right here, 1 plus 0.12 over 4. If you put that into your calculator, you get T equals 1.03 4T. And this is where I was talking about. Notice the unknown is in the exponent. So that means we are going to have to apply natural logs. All right, so what we're going to do is, as long as in equations, whatever you do to one side, you do the exact same thing to the other, then it is allowed. So we're going to take the natural log of both sides. So the natural log of 2 equals the natural log of 1.03 raised to the 4t. Now we're going to start applying our properties. Well, there's no property that goes along with this. It's just a single natural log, so we're okay. Here, I'm going to take this exponent and move it over here. And of course, that is applying this property right here. So that would give us the natural log of 2 equals 4t times the natural log of 1.03. Now, our goal is to find out what t is, so I want it by itself on this side of the equation. So we have 4 times t times the natural log of 1.03. So to undo multiplication, we're going to divide. What do we want to get rid of? We want to get rid of the 4 as well as the natural log of 1.03. Whatever you do to one side, you have to do to the other. So these cancel and we're left with t. And then of course, now we go to our calculator and we would have the natural log of 2 over 4 times the natural log of 1.03. And so I'm going to round that to 2 decimal places. So 5.86. And if you remember, time is always in years. So this represents approximately 5.86 years. Now, what if you were asked to convert that into years and months? Well, we know we have 5 years. I need to be able to convert the 0.86 into months. How do you do that? You just multiply it times 12 months in a year. So what 0.86 means is 0.86 of a year. There's 12 months in a year, so it would be approximately 10 months. So approximately 5 years and 10 months. Okay, now I want to jump back up here in this. In this first example, I show you this, and of course, when you're doing these problems, you can always put p here, and here you could put 2p, 3p, 1.5p, but you'll always divide by p first, which means the p's will go away. So this, remember I said p was 100% or 1. This is like 1, and if you double it, it is 2. So you don't have to start out here if you recognize that from the very beginning. It just depends on what you recognize. If you need to see it, by all means, do it. Okay, another example. You're going to buy a house. Whoops, can't spell buy this morning. And you purchase this house for $40,000. 15 years later, you sell for $100,000. So good deal, went up in value. If interest is compounded continuously, what rate did the 40,000 earn? All right, so we need to take a look at this one because it's not exactly like the one I just did, okay? So 15 years, yeah, that's pretty easy to figure out that we know, okay, t is equal to 15. Now, notice it is asking for what rate. So the rate is the unknown. Now, the other thing that you need to look at is that it is compounded continuously. So that means we do not have an M. When it's compounded continuously, you're looking at these, okay? So we know we're going to use the one with the E in it. Now, what we do have is $40,000, all right? So $40,000 is your initial amount. So that is your P, that is your initial amount, and in this case, it is $40,000. $100,000. So then the later amount, okay, the later amount, which is your future value, is 100,000. So when I look over here, I know I'm going to be using these two. Later amount would be future value. So value after T years. So ours would say value after 15 years. So here's going to be the 100,000. My initial amount was the P, which is the 40,000. So we know we are going to have 100,000 equals 40,000 e to the r times t. So r is what we're looking for. All right, so just like we did in the last one, our unknown is in the exponent, so we're going to have to apply natural logs. But when you're dealing with e, before you apply natural logs, always isolate the e. That means be sure the e is on that side by itself. It cannot have a coefficient in order to, you have to eliminate the coefficient or get rid of it before you can apply natural logs. So we have 40,000 times this. So to undo multiplication, we're going to do its opposite, which is divide. So we're going to divide both sides by $40,000. And 100,000 divided by 40,000 is 2.5. And over here, we're left with e raised to the, I'm just going to rewrite that as 15r. Okay, so now our unknown is in the exponent. So what do? We take the natural log of both sides. Whoops, I about put 2.5 there again. Sorry. Now, over here, it's a single natural log, so we're going to leave that alone. But here, this exponent, why did I do this? So I can move this over here. So I have the natural log of 2.5 equals 15r times the natural log of e. Well, guess what? Get very familiar with recognizing that the natural log of e is equivalent to 1. So I have the natural log of 2.5 equals 15r times 1 is just 15r. Divide both sides by 15. And so you get, let's see, I think you get 0.061086 to convert it into a percentage. Now, it just depends then on how far WebAssign asks for. I'm going to say that R is approximately 6.11%. So that is the rate. All right. One other type of example that you're going to encounter, and if you'll look over at your formula sheet, it deals with this right here, proportion of C14 remaining after T years, and it tells you what it's equal to. All right, well, what is C14? C14 is carbon 14 dating. Okay, so that formula is in the future. It will be P-E raised to the negative 0.0001238t. That's quite an exponent, okay? So here's an example. 22% of the original amount of C14 is remaining estimate the age in two significant figures. Now I'll explain what that is at our final answer. All right. Okay, so we're going to apply this right here. Okay. Estimate the age. So what we don't know is t. So the unknown is t. All right, that means we need to figure out what p is and what the future value is. Now remember, p is 100%. This would be 22%. Okay, so not an increase of 22%. Here's what that means. P is your initial amount, which is 100% or 1. Your future value, it is not increasing by 22%. It just means that 22% is what is left. So that's just going to be 22%. This isn't financial where we're increasing an account, okay? All right, so what that means is we have 0.22 is equal to 1 times e to the negative 0.00012338t. So 1 doesn't have to be there. I go, okay, in essence, my e is isolated. You could divide both sides by 1, but it's not necessary. So my e is isolated, so I can go straight to taking the natural log of both sides. So applying my properties, bring that to the front, or if you recognize right here, you can just set it equal to that exponent. You wouldn't even have to do this, but I'm going to go ahead since I already wrote it. Natural log of 0.22 equals negative 0.00012338t times the natural log of e. This is the same thing as 1. So if you'll notice, the shortcut would have been just to recognize that the natural log of e raised to that is just that exponent. And if I want t by itself, I'm going to divide both sides by about 0.00012338. So t equals, so I would go to my calculator, the natural log of 0.22 over negative 0.00012338. And I get 12230.43403. All right, so if you recall, this said estimate the age in two significant figures. What that is basically asking you to do is to put it into scientific notation. And scientific notation means move your decimal after your first whole number. So that would be 1.2 times 10 to the 1, 2, 3, 4. We move the decimal 4 places. So just in case it asks you that. Okay, there we go.